Okay, here we're looking for the pressure exerted on this patient's vein by this fluid here that's hanging in this bag. And first, I should be clear that really what we're looking for is the gauge pressure, the relative pressure of the fluid in this bag relative to his arm, right? Because we have the pressure varies with depth. The pressure increase due to depth is just rho gh, right? So P is equal to P naught plus rho gh, right? So this is how much it increases with depth. If we have here, let's say that we have up at the top, this is P naught, which is maybe atmospheric pressure. Well, on the outside, his arm is going to be basically the same pressure here, and it's going to be basically P naught, right? When you look at the pressure difference between the pressure in here, which is going to be P naught plus rho gh, and then I subtract out the pressure in his arm because I'm really looking for the net pressure on his veins, not the absolute pressure. And then I'll subtract out a P naught, right? And I'll just have rho gh. So really because this will be at atmospheric pressure, because this at the top up here is going to be at atmospheric pressure, and his arm is also at atmospheric pressure. And also, there's not a big height difference here, right? I mean, he's laying lower, so technically he just atmospheric pressure alone, he has a little bit greater pressure, rho gh, but the density of air is only about 1 kilogram per cubic meter. And G and H are the same, but then the density of this fluid is 1,060 kilograms per cubic meter. So the pressure in here is 1,060 times the pressure out here. So it's really not worth mentioning that pressure difference, from the air outside. Now, if this were, the top of, regardless of the height, it's the density that makes a difference there. So unless he was laying underneath a fluid of pressure of density 1,000 kilograms per cubic meter or something like that, then it's not gonna it's not gonna matter to just take the pressure increase due to the air into consideration. Okay, so basically we're just looking for the gauge pressure, which is just going to be rho gh, right? Rid of the pressure increase due to depth, the gauge pressure there. It gives us a height, it gives us a density, and we have G, right? So we can just use here the pressure in his arm is going to be rho gh. Of course, then H is in meters. Rho is in cubic meters, and so this is good. But we actually wanted it expressed in millimeters of mercury. So we'll calculate it and then we'll convert it to torr at the end. So the pressure here is going to be equal to rho gh. So we have 1,060 kilograms per cubic meter, and then we have times 9.8 meters per second squared, and then the height of 1.2 meters, right? Well, so positive H is taken downwards when we're talking about pressure increase, right? So pressure always increases downwards. So this is a downwards height for this equation. And this is 1.2 meters, right? So we end up here with the pressure will be in pascals. And this comes out to pressure here is 12,465.6 pascals, okay, or newtons per square meter. Of course, then we want to convert this to millimeters of mercury, so then I multiply by, let's see, on the bottom I have 1.013 times 10 to the fifth pascals, so that way this cancels, and then I have 760 torr, or 760 millimeters of mercury on the top. And doing the conversion here, we have the pressure on his arm. This net pressure on his arm is 93.5 torr, right? or 93.5 millimeters of mercury.